Hi, my name is Vikram Sivasalam and I am from Continuum Blue Limited, a Comsol certified consultant. Today, I'll be presenting our cable builder tool which helps to build subsea cable models for analysis. With thousands of miles of subsea cable being produced each year and laid across the world's oceans, it is important to ensure that these cable structures are designed to take the load that they are exposed to during installation or service. This is where subsea cable manufacturers can, with the help of our cable builder tool and Comsol multiphysics, analyze and assess their cable designs under various load conditions. Allow me to demonstrate the use of our cable builder tool, which can, from client-supplied cross-sectional drawings and a specification sheet, build a full Comsol multiphysics model ready for stress and fatigue analysis. Here is a typical example of a subsea cable cross-sectional drawing which details the design requirements of the cable. These include external reinforcing structures which can be woven Kevlar layers or multiple layers of counter-rotating steel armor wires as seen in this design. In this particular design, we have a number of hydraulic hoses as illustrated by the numbers 1 to 5. Some quad cores and data cables as illustrated by these items here. In addition to these, there are also a number of fillers and rope ballasts which help maintain the structural integrity of the cable design. From this drawing file, we can obtain dimensional details and component layouts as required in the design. The client also supplies a specification sheet which describes the materials present in the system and the load cases that needs to be assessed. Once the drawing file and the specification sheet have been provided, we can then use the Continuum Blue's cable builder tool to generate the complete Comsol model ready for analysis. Here is the interface of the cable builder tool. The tool is developed in MATLAB and uses LiveLink for MATLAB to seamlessly integrate with Comsol multiphysics. We start using the cable builder by clicking on the button marked Input Data from the specification sheet over here. Then we locate the project specification sheet and click Open. This will then provide the input data to build a schematic of the cable cross-section, highlighting the various predefined components as shown in the 2D image. Once assessed, a window pops up asking if this is the correct cable cross-section. We can then compare the schematic against the supplied drawing to ensure that this is the case and that all the components are correctly positioned. There are panels below the image to help assess and compare the cable design requirements, such as color key for the components, internal and external dimensions of the cable, and lay data such as pitch lengths of various cable layers. You will notice that only half of the internal components are shown. This is because the cable builder tool assessed that symmetry is applicable. Once happy, we can then proceed by building the symmetric section of the model by clicking on the symmetric tick box here and selecting the appropriate symmetry condition. This then generates the full cross-section of the cable in 2D as well as generates a 3D representation of the cable design. While generating these, the cable builder also checks the internal structures to ensure that there are no issues such as intersection or overlapping components. If there is an issue, a message will be displayed indicating that a problem was found and the user is required to check the design specifications. If no issues are found and we can confirm that this is indeed the correct cable layout, then we are in a position to generate the Comsol model. This is simply done by clicking on the Generate Cable button. This model took just over 6 hours to generate. Once complete, the user is presented with a complete Comsol model as illustrated here. The model comes in fully parameterized and makes use of selections, probes, and other Comsol features. The complete list of parameters is shown here and includes parameters for dimensions, study loads, material properties, meshing, solver settings, and much more. In addition to this, there are a number of switches implemented in the parameter section to help the user activate or deactivate or control certain nodes in the model, such as displacement constraints. To highlight some of the features, we will drop down the model tree and investigate further. In the probe section of the Cleat, a number of probes have been implemented, such as maximum stress, which can be monitored during the analysis. A list of selections is also made to identify different components and material groups. Since there are hundreds of components present, assigning materials to each of them can be a tiring process. However, in the materials section, the materials are fully defined and make use of selections created along with the material parameters already defined in the parameter list, making things effortless. The Cleat model built by the cable builder also features 3 available mesh options, as seen here. As I mentioned earlier, mesh parameters have been implemented in parameter section of the model tree, allowing the user to have complete control of the mesh. A number of study options are also implemented in the model, giving the user a choice of studies with pre-built solvers and scaling of dependent variables, all controlled from the parameter and variable section. Once the user has finished running a study, a number of pre-built plots are available to visualize the results. These plots also come with their own view settings, again controlled from the parameter section. These view settings automatically hide certain domains and/or boundaries based on the selections to ensure that the results plot only display the appropriate plot regions and components. Included in the results section are a number of export features which output the results into the project folder, helping us to provide our clients with images and animations as per their requirements. Some examples of these exported images are illustrated here. We at Continuum Blue also perform analysis on subsea rises, cable joints, and thermal analysis on substations. This concludes my presentation on the Cable Builder tool, a tool to build Cleat multiphysics models faster, smoother, and most importantly, cost-effective for subsea cable analysis. I'm going to discuss how we at Continuum Blue use Cleat to do modeling for the analysis of cable cleats. Cable cleats are heavy-duty components used to tie down medium to high-power cables. In this example, we are going to see a simple trefoil cable cleat design used to constrain 3 power cables, each carrying a single-phase peak current of over 150 kA, 120 degrees out of phase with each other during an instantaneous short circuit of the system. Power cables which carry the high currents across when instantaneously short-circuited would produce incredibly high electromagnetic forces, which could tear them apart and potentially damage or even worse, fracture the cable cleat. Thus, it is important for the cable cleat manufacturers to ensure their design can withstand the possible loads placed on them during a short circuit. Failure to do so could result in catastrophic damage to equipment and buildings. Here at Continuum Blue, we have the capability, with the help of Cleat multiphysics, to assess and analyze cable cleat designs prior to prototyping or manufacturing to ensure they can withstand the required loads placed on them and obtain certain safety ratings. Additionally, with the use of finite element analysis, it gives us the ability to identify critical areas of the cleat designs, be this geometric or material, which may require redesign. Here is a simplified trefoil cleat Cleat model used to constrain 3 power cables during short circuiting. As can be seen, we only show a section of the 3 power cable for analysis requirements. In this model, we make use of a number of coupled physics to model the system. These include structural mechanics and electromagnetic. The structural mechanics section makes use of nonlinear material models such as plasticity for the copper in the cable and steel cleat. Additionally, hyperelastic material models for the polyurethane sheets used to insulate the power cores. These are coupled to the AC-DC module and electromagnetic features of Cleat to produce the electromagnetic forces on the cable during short circuiting. Once the time-dependent analysis has run, we can obtain results for the directions, the electromagnetic forces acting on each cable as illustrated by the vector plots in the animation on the left. The color regions of the copper cores of the power cable illustrate the force magnitude on each core. The animation in the middle shows the resulting displacements on the cable due to the forces exerted. And the plot on the right displays the von Mises stress of the simple steel cleat. In short, using our multiphysics model for Cleat design and short-circuiting of power cables, engineers are able to assess their designs to ensure they do not fail before prototyping or manufacturing. I'm going to discuss how we at Continuum Blue use Comsol to do modeling for automotive industries. To illustrate this, I'm going to show you how we perform thermal stress and fatigue analysis of a heat exchanger used on the railway. This is a CAD of a heat exchanger provided to us by one of our clients. As you can see, the design is very complex and it involves a number of components. And not to forget, there are hundreds of bolts present in the system. Once the CAD is built, we then use LiveLink for SolidWorks to import this CAD directly into our Comsol interface, thereby making life easier. Comsol also gives us a number of other features which can be used to edit the geometry built. For example, ignore edges and virtual operations are used to remove unwanted boundaries and edges. We then set up the parameters required, like geometry-related parameters or material-defining parameters inside the parameter section. We also use specific variable sections to specify variables needed to be solved for during the simulation. Selections and probes are also set to make things easier to set up the model. With so many components in this model, one can easily imagine the number of contact sets and the boundary conditions to be applied. Here is a list of contact pairs that we use. We also make use of identity pairs wherever necessary. Having so many components and each operating at different temperatures, the material characteristics are not easy to set up for thermal fatigue. Thanks to Comsol, using the function feature inside the material section, we can make material characteristics to be temperature dependent. Having made the selections before and with the material parameter set, implementing the material properties for different components is made even simpler. Since we performed fatigue analysis of the system, we also have SN curves set up to help us analyze the fatigue life under various loads. Since the design of the system is very complex, the mesh is not going to be easier either. However, at Continuum Blue, we with our vast experience in meshing have meshed the system as best as possible. Here is what the mesh looks like. Coarse mesh has been used wherever possible to run the simulation quicker. As we perform a thermal stress analysis of the heat exchanger, we use the thermal stress physics already available in Comsol. With so many components, setting up the boundary condition is a difficult task. However, Comsol has provided us with some built-in features which make this look effortless. Depending on the client's requirements, a number of studies have also been set up. Here, 3 studies have been created. Static for proof and thermal stress analysis, dynamic for fatigue analysis, and a time-dependent study for analyzing stress levels at different time points of the cycle. Predefined plots have been also set up based on the client's needs. Specific views are created so that the clients can visualize results depending on different material groups. Thanks to Comsol once again, we use the export feature to export the images to set location while the results are plotted. All these things make the simulation so easy that not only do we provide accurate results, but also perform them faster, thereby reducing time and most importantly, the cost to our clients.